Hello and welcome to the Chapter 10 intro video. Chapter 10 is on the topic of gases. The next three chapters will be on the topics of gases for Chapter 10, talk about liquids in Chapter 11, and finally, you guessed it, solids for Chapter 12. So in Chapter 10, we're going to talk about the characteristics of gases, talk about pressure, the gas laws, the ideal gas law equation, and some applications with this equation, gas mixtures and partial pressures. We'll talk about the theory of the kinetic molecular theory of gases to try to understand their behavior, and then talk about diffusion and diffusion, and finally get into real gases. Okay, so let's look a little bit deeper here. Pressure can be defined as the force that's exerted onto some square surface or some surface area. Okay, we can think about pressure in terms of pressing on an object. So when we're pressing on the surface area of the object with some amount of force. You might think about force because this is a mass times the acceleration of that mass. So that's what force is equal to. And area, you might think of this as some sort of square meters in terms of the unit here, in terms of how we think of the area. Okay, so the mass is the kilogram, and the acceleration is meters per second squared. So if we think about our units for pressure, we'd be plugging in a kilogram meter per second squared for the force, and then that would also be the unit of the 1 Newton. So 1 Newton is a kilogram meter per second squared, and then dividing that by an area in units of square meters. And so that if we do our cancellation here, we see that one of these cancels in that pressure. We have this unit of kilogram, meter to the minus 1, second to the minus 2. These are the fundamental SI units behind the SI unit of pressure that we define as the Pascal. So 1 Pascal is equal to 1 kilogram meter to the minus 1, second to the minus 2. Now we might recall that our joule kind of is defined in a similar way as being 1 kilogram meter squared per second squared, and then even lastly the Newton, more for physics here, but 1 Newton is equal to 1 kilogram meter per second squared. And you could write per second squared or second to the minus 2 in this way here. And so obviously gases behave in such a way that they conform to the shape of their container. We're going to see that the gas particles mostly behave independently of whatever the constituent is that makes up the gas. So the key sort of property for gases is how many particles are present within the gas. So we're going to see that a gas is really just described by how much gas there is, what its temperature is, and what the volume of the gas happens to be. Now, a few ways we encounter gases. One is just through atmospheric pressure. So we are underneath a pressure of about 1 atm, that's standard atmospheric pressure. And in terms of thinking about the amount of air that there is on top of every square meter on the surface of Earth, the answer is about 10 to the 4th kilograms. Now you could work this out in, if you have some way of approximating the atmospheric mass and also the surface area mass, you can get a sense of how much mass there is accelerating towards the surface area of Earth due to gravity. So the gravitational force is what's pulling the atmosphere towards the surface of the Earth, and hence is part of the surface pressure that we feel at the base of Earth. And so if we have 10 to the 4th kilograms that are being exerted with the velocity of gravity, so about 9.8 meters per second squared, and then we're going to have that pressing on every square meter, that this works out to be approximately equal to 10 to the 5th kilograms meter to the minus 1, second to the minus 2. So our standard atmospheric pressure in units of pascals would be about 100,000 Pascal, is approximately equal to what we call our standard atmospheric pressure, or within the unit of ATM, 1 ATM. Now we can give some more precise conversion factors, and we're going to not always deal with different pressure units, but a few times in this chapter we might see a few different units for pressure. So 1 ATM is exactly equal to 760 torr, so that's exact. It's also equal to another unit that's synonymous with torr, that's millimeters of mercury. So two different ways of really just saying the same unit of millimeter of mercury or torr. And then another unit is this Pascal unit, so more precisely, it's 101,325 exact Pascal in 1 atmosphere. And then lastly, one other unit, we have 1.10325 bar. The bar being a unit that's a little bit more commonly used in meteorology. So a few different types of units that we tend to encounter. We can actually give one other unit of PSI, that this would be equal to 14.696. 14.696 pounds per square inch. Now the pounds per square inch is just an interesting unit because you're thinking of the force in terms of the pounds of pressure that are exerting onto a square inch. So it's just your slightly different unit for pressure that sometimes we encounter. So there's a few different ways that we relate some properties of gases. So the sort of main properties that we can use to describe a gas we'll find are the pressure, the volume, the quantity, so the moles, and then of course the temperature. So these are the sort of 4 characteristics that tell us just about everything we need to know about a particular gas. Now there's some relationships between these properties that have been observed. For example, Boyle's law found a relationship between pressure and volume, that they were inversely related. So if you decrease the volume of a gas, so if you imagine having like a piston that you can pressurize a gas, if you press down on it, you're increasing the pressure. So by reducing the volume of a gas, so if you imagine you have some sort of container, you have a piston that you can press down upon, if you press down and decrease the volume, then that serves to increase the pressure. So there's this inverse relationship between pressure and volume as found by Boyle. Charles' law found a relationship between volume and temperature. So if you could take a gas and change its temperature, you can find a relationship to volume. So if we could increase the temperature of a gas, then we have to increase the volume. So if you imagine having a container that has, say, a movable piston, so this piston can go up or down depending on the pressure of the gas, or the temperature of the gas. If we increase the temperature of the gas, the piston moves upward, the volume expands. We lower the temperature, the piston contracts. And what the piston is doing is just maintaining a constant pressure inside of the container. So if we increase temperature, we increase the volume of a gas, and then vice versa. If you lower the temperature, you lower the volume of a gas. And finally, Avogadro studied a relationship between the volume and the quantity. So if you just add more gas to the container, then we need to expand the volume if we're going to keep the pressure and the temperature the same. So increase the quantity of the gas, so put more gas in the container, more moles in it, then we're going to increase the volume of the container. So let's take a look at the relationship between volume and the other quantities. So volume is directly proportional to 1 over pressure. So again, if you increase the volume of a gas, you are decreasing the pressure and vice versa. And then you also have that volume is directly proportional to the quantity and to the temperature. And so what we can write is that V is directly proportional to NT divided by P. And then you can also then determine that PV over NT, just doing a little cross multiplying, is therefore just equal to some constant, where if we take these 4 quantities and relate them for any gas, they come out to be equal to essentially the same gas constant as long as the gas is obeying what we call the ideal gas law. The main idea behind the ideal gas law is that if your particles of a gas are non-interacting particles, the only thing that really matters is how many actual gas particles there are within a sample. So if you imagine having, say, you have 1.00 moles of a gas like O2 or helium or CH4, just one of these gases, or any other gas, that all that really matters is if you have CH4, you have an Avogadro's number of methane molecules. If you have helium, you have an Avogadro's number of helium atoms. If you have a mole of oxygen, you have an Avogadro's number of oxygen molecules. What really matters is just how many of these particles you have within your gas mixture. It doesn't really matter how many atoms there are within the particle. What really matters is how many actual particles are there. because 1 mole of any gas, any say of these 3 gases or any other gas for that matter, at STP, and STP is 1 atm, 0 degrees C, has a volume of 22.415 liters. This is sort of a finding that Avogadro found a long time ago. So no matter what gas you have a mole of it, the gas occupies essentially the same volume if you have an atmosphere of the gas at 0 degrees C. If we ever say STP, just remember the temperature there is 0, not 25 degrees C. Okay, and so if you throw in these units in terms of 1 atmosphere, 22.415 liters, plug in a mole, throw this into Kelvin. You got to go to 273.15 Kelvin for this quantity here. So plug in a mole, plug in 22.415 liters, plug in a mole of the gas, and then you get that the R, the ideal gas constant, is equal to 0.08206 liter atmospheres per mole Kelvin. Now you can convert pressure to different units and calculate R and other types of units, but this is the most commonly used one. The liter atmospheres per mole Kelvin are the units here. And so that's how we solve and determine the ideal gas constant and then relate that to the pressure, volume, and the number of moles and the temperature. So some applications of the ideal gas law are that we can change our initial set of these conditions. If you take any of these variables and change them, so say you change the pressure, you have to change at least one of the other variables accordingly. Because the P1 V1 over N1 T1 our initial set of conditions are equal to the ideal gas constant, then after we make our changes, those changes are still equal to the ideal gas constant, so they're equal to each other. Now, we could leave or have one of these variables perhaps remaining constant. Let's say we're changing the pressure and the volume and the quantity of a gas, but keeping the temperature constant. If the temperature is constant, temperature cancels. If we keep the volume constant, then then the volume cancels. So like one way we can sort of consider a relationship between pressure and moles is the pressure and the moles are directly related to each other. If I put more gas into a container at constant volume and temperature, then the pressure has to go up. So we can think of different relationships between some or all of these variables. Like let's say we're only keeping the quantity of gas constant, and then we're changing the pressure and the volume, and then we're going to have to see a change in temperature as well that accompanies this. So we could write that P1 V1 over N T1, if moles are constant, is equal to P2 V2 over N T2. If the moles aren't changing, then the N cancels out. So we have P1 V1 over T1 equals P2 V2 over T2. So we can solve problems where we're changing 2 or more of the variables and consider what they're going to be after the change occurs. And then another thing we can do is maybe give you 3 of the 4 variables and have you calculate the 4th. So we could give you 1 of the variables and then you can solve, or give you 3 of the 4 variables and you can solve for the 4th. So let's talk about gas mixtures and partial pressures. So let's say we have a mixture of O2 and N2, which is essentially air. So let's say we have 0.21 atm of O2, 0.78 atm of N2. And then let's say we have 0.01 atm of, let's say, argon. Turns out that this is about the makeup of air. But that our total pressure would just be the sum of our components. So we just take the partial pressure of O2 plus the partial pressure of N2 plus the partial pressure of argon, which actually turns out to be the 3rd most abundant substance in the atmosphere. If we add all these up, we're going to see that we end up getting 1.00 atm. And then everything else is just less than about 1% of this mixture of air that we're breathing in all the time. Now, one of the things that we could do is relate or try to say, well, how can we relate the partial pressure of a component to how much of that gas is actually present within the mixture? And so now we can deal with gas mixtures in, like say, an air sample, but also any other gas sample we might encounter. And so one of the things we might want to do is just compare, well, what's the partial pressure of one component of a mixture compared to the total partial pressure? Well, if we say, relate the pressure of one component, we probably can remember that PV is equal to nRT. So the pressure of component 1 would be equal to the moles of component 1 times RT, and then dividing by V, the volume that the gas is occupying, and then dividing that by the total number of moles times RT divided by V. Now, since the gas mixtures are in the same container, they're at the same temperature and at the same volume. So those, and of course the ideal gas constant itself cancels as well. So we have this relationship here that the partial pressure of one of our components would be equal to the mole fraction of that component times the total pressure. Okay, so N1 over NT is defined as the mole fraction of that component, of say component 1. So X is the mole fraction. So just the mole of that particular component divided by the total number of moles. Okay, so you take the mole fraction of a component times the total pressure. That gives you the partial pressure of that particular component. Let me also change this. Usually we use Ni here, not N1. So let me change these to I. So the partial pressure of component I compared to the total pressure is the moles of I times RT divided by V divided by the total number of moles times RT over V. And so then RT over V cancels, so we have Ni over NT is the partial pressure of I is equal to the mole fraction of I times the total pressure. So we'll relate some properties of partial pressures and use this relationship here with the partial pressure. This is Dalton's law of partial pressures. So the kinetic molecular theory of gases is a set of about 5 postulates that hopefully can help us better understand how gases behave. The first postulate says that gases are essentially non-interacting particles in random motion. So a gas sample contains particles that are all moving around inside the container constantly. They may bump into each other, but the particles are non-interacting. So postulate number 2 says that the combined volume of the particles of the gas is negligible. So the volume occupied by particles in a gas mixture is negligible. So the container is mostly empty space is the idea. So if you have a gas sample, the actual particles themselves occupy such a small amount of the container that the amount of space they're taking up is negligible and doesn't need to be considered. 3 is that the attractive and repulsive forces between the particles are negligible. So this means that the particles themselves are not interacting with each other in a beneficial, attractive way or in a repulsive way either. So the particles are simply non-interacting. So energy can be transferred, but the average kinetic energy of the molecules over time cannot change. So collisions can occur, but energy is conserved. So a fast particle might strike a slow particle, but then the slow particle moves faster, and then the faster particle reduces its speed at the same time. Now the average kinetic energy of the particles is proportional to their absolute temperature. So what this is helping us understand is that if we increase the temperature of a gas sample, what we're really doing on average is increasing the average kinetic energy of the particles. Now, kinetic energy is equal to 1/2 mv squared. So if by increasing temperature means we increase the kinetic energy of the particles, the mass of the particles is a constant, so we're then could cause an increase in the average velocity of the particles. So the velocity of the particles on average is simply related to their temperature. So if you increase the temperature of a gas sample, then the particles are going to move around the container with a higher velocity. Now if you start thinking about what causes pressure, it's the force that those particles are applying on the surface walls of the container. So if you have a container that's filled up with a gas, so just picture a container filled up with a gas. If you increase the temperature of the gas, you're just causing more collisions with the container. So you're increasing the pressure of the container due to the temperature going up, the average kinetic energy of the particles, their velocity goes up, there's more collisions with the wall of the container. If you add more particles of the container, same thing. You're just having more collisions occur with the container wall, so you have a higher pressure. So let's talk about effusion and diffusion and a little bit more about the velocity spread of molecules. So effusion is the rate at which a gas escapes from like a pinhole. Imagine a hole in the tire. How long does it take the gas to escape? That's related to effusion. Diffusion is like the scent or the smell. It's like a compound spreading out over other molecules. So imagine like somebody's cooking in a kitchen. How long does that smell take it to reach the upstairs of your house, for example? That spreading out of a gas through a medium is diffusion. And so you can sort of understand or probably appreciate that if a particle has a higher velocity, it's going to effuse and diffuse faster. So a particle is going to, on average, have a higher rate of effusion and diffusion if it's simply hotter. So if you increase the temperature of an object, you're just increasing the average speed. So you have more particles that are traveling faster, so you're going to get faster effusion and diffusion. You could also imagine molecules that are simply lower in molecular weight, on average, are going to travel faster as well. One way we can track speed is by comparing things like the most probable average or the root mean square speed. So the speed that's most probable is the top of the curve. Our average is a little bit higher of a velocity. It's the speed at which the average molecules have. So if you just take a simple average of all the molecules, that's the average velocity. And then the root mean squared velocity is the speed of a molecule whose kinetic energy is equal to the average or mean kinetic energy of the molecules. The VRMS has a nice relationship to the ideal gas value R. So 3RT divided by the molar mass. Only issue is that R here is equal to 8 or the best way to plug R in to actually get a reasonable set of units out here is 8.314 joules per mole Kelvin. Plug those in for your units of R, plug T in, of course, in Kelvin, and then plug your molar mass in kilograms, and you can calculate the actual root mean square velocity. Now, one of the keys is if you see the relationship here is that if you have a lower molar mass, you're going to have a higher root mean square velocity than for your gas. So gases that are lighter simply travel with a higher velocity. As well, higher temperature, higher velocity as well. So if you can increase the temperature or reduce the molar mass of your gas, it's going to effuse or diffuse more quickly. Now finally, we get deviations from ideal gas behavior under two different types of scenarios. One is when we have the volume of the particles break down. So whenever the volume of the particles occupy a non-negligible amount of the container, this is a high pressure problem. If you have a gas at a high pressure, the particles are going to begin to occupy a reasonable portion, a non-negligible amount of the container. So that's going to happen whenever you have a lot of gas present within your sample. Then another issue happens when the gas particles start to be attracted to each other. And so the other place where we get deviations in ideal gas behavior is at the point at which the molecules start to become attracted together. So molecular attraction begins to occur as we approach boiling point. So these are a low temperature problem. So two different issues, two different scenarios when we tend to have deviations from ideal gas behavior, whenever the volume of the particles begins to occupy a non-negligible portion of the container at high pressures, and then whenever the molecules begin to have an attraction for themselves. Now, the fact that gases eventually, most of them can liquefy, well, I mean, they can all liquefy, it's just a matter of what temperature. Some of them are going to be at higher temperatures than others. Helium is the lowest boiling substance. Its boiling point's about 4 Kelvin. So you get it cold enough, eventually it will liquefy. So even something like helium can sense an attraction for itself, but even at a really, really low temperature. So the key is you're going to get breakdown in ideal gas behavior because your particles are now sticking together. So your particle count, by just taking the number of moles of your gas sample, kind of breaks down once some of the particles are sticking together. So there's an equation that helps us relate and solve these particular problems. But for where we're at in the class right now, we get this ideal gas breakdown whenever our molecules are sticking together due to intermolecular forces. And this is going to be more predominant at higher temperatures for molecules that are polar, and for molecules that can do things like form hydrogen bonds that just have strong attractions for themselves, like in the case of water. So this is going to lead into, the formation of liquids, and then the next chapter into talking more about the forces that hold liquids together in terms of intermolecular forces. So that's all for an introduction video. It's a little bit different way I did the video this time. Hopefully this helps you get ready for class on Friday this week. All right, thanks for the attention.